Longitude is a geographic coordinate that specifies the east-west position of a point on the Earth's surface. It is an angular measurement, usually expressed in degrees and denoted by the Greek letter lambda. Points with the same longitude lie in lines running from the North Pole to the South Pole. By convention, one of these, the prime meridian, which passes through the Royal Observatory, Greenwich, England, was intended to establish the position of 0 degrees longitude. The longitude of other places was to be measured as the angle east or west from the prime meridian, ranging from 0 degrees at the prime meridian to plus 180 degrees eastward and minus 180 degrees westward. Specifically, it is the angle between a plane containing the prime meridian and a plane containing the North Pole, South Pole and the location in question, pointing from the Earth's center toward the North Pole and the x-axis extending from Earth's center through the equator at the prime meridian. A location's north-south position along the meridian is given by its latitude, which is the angle between the local vertical and the plane of the equator. If the Earth were perfectly spherical and homogeneous, then longitude at a point would just be the angle between a vertical north-south plane through that point and the plane of the Greenwich meridian. Everywhere on Earth the vertical north-south plane would contain the Earth's axis. But the Earth is not homogeneous, and has mountains, which have gravity and so can shift the vertical plane away from the Earth's axis. The vertical north-south plane still intersects the plane of the Greenwich meridian at some angle. That angle is astronomical longitude, the longitude you calculate from star observations. The longitude shown on maps and GPS devices is the angle between the Greenwich plane and a not-quite vertical plane through the point. The not-quite vertical plane is perpendicular to the surface of the spheroid chosen to approximate the Earth's sea level surface, rather than perpendicular to the sea level surface itself. History. The measurement of longitude is important both to cartography and for ocean navigation. Mariners and explorers for most of history struggled to determine longitude. Finding a method of determining longitude took centuries, resulting in the history of longitude recording the effort of some of the greatest scientific minds. Latitude was calculated by observing with quadrant or astrolabe the altitude of the Sun or of charted stars above the horizon. But longitude is harder. Amerigo Vespucci was perhaps the first European to proffer a solution. After devoting a great deal of time and energy studying the problem during his sojourns in the New World, as to longitude, I declare that I found so much difficulty in determining it that I was put to great pains to ascertain the east-west distance I had covered. The final result of my labors was that I found nothing better to do than to watch for and take observations at night of the conjunction of one planet with another, and especially of the conjunction of the Moon with the other planets, because the Moon is swifter in her course than any other planet. I compared my observations with an almanac. After I had made experiments many nights, one night, the 23rd of August 1499, there was a conjunction of the Moon with Mars, which according to the almanac was to occur at midnight or a half-hour before. I found that, at midnight Mars's position was 3.5 degrees to the east. By comparing the positions of the Moon and Mars with their anticipated positions, Vespucci was able to crudely deduce his longitude. But this method had several limitations. First, it required the occurrence of a specific astronomical event, and the observer needed to anticipate this event via an astronomical almanac. One needed also to know the precise time, which was difficult to ascertain in foreign lands. Finally, it required a stable viewing platform, rendering the technique useless on the rolling deck of a ship at sea. See lunar distance. In 1612 Galileo Galilei demonstrated that with sufficiently accurate knowledge of the orbits of the moons of Jupiter one could use their positions as a universal clock, and this would make possible the determination of longitude. But the method he devised was impracticable for navigators on ships because of their instability. In 1714 the British government passed the Longitude Act, which offered large financial rewards to the first person to demonstrate a practical method for determining the longitude of a ship at sea. These rewards motivated many to search for a solution. John Harrison, a self-educated English clockmaker, invented the marine chronometer, a key piece in solving the problem of accurately establishing longitude at sea, thus revolutionizing and extending the possibility of safe long-distance sea travel. Though the Board of Longitude rewarded John Harrison for his marine chronometer in 1773, chronometers remained very expensive and the lunar distance method continued to be used for decades. Finally, the combination of the availability of marine chronometers and wireless telegraph time signals put an end to the use of lunars in the 20th century. Unlike latitude, which has the equator as a natural starting position, there is no natural starting position for longitude. Therefore, a reference meridian had to be chosen. It was a popular practice to use a nation's capital as the starting point, but other locations were also used. While British cartographers had long used the Greenwich meridian in London, other references were used elsewhere, including El Hierro, Rome, Copenhagen, Jerusalem, St. Petersburg, Pisa, Paris, Philadelphia, and Washington, D.C. In 1884, the International Meridian Conference adopted the Greenwich meridian as the universal prime meridian or 0 point of longitude. Noting and calculating longitude. Longitude is given as an angular measurement ranging from 0 degrees at the prime meridian to plus 180 degrees eastward and minus 180 degrees westward. The Greek letter lambda is used to denote the location of a place on Earth east or west of the prime meridian. Each degree of longitude is subdivided into 60 minutes, each of which is divided into 60 seconds. A longitude is thus specified in sexagesimal notation as 23 degrees 27 minutes 30 seconds east. For high precision, the seconds are specified with a decimal fraction. An alternative representation uses degrees and minutes, where parts of a minute are expressed in decimal notation with a fraction, thus 23 degrees 27.500 e. Degrees may also be expressed as a decimal fraction, 23.45833 degrees east. For calculations, the angular measure may be converted to radians, so longitude may also be expressed in this manner as a signed fraction of pi, or an unsigned fraction of 2 pi. For calculations, the west-east suffix is replaced by a negative sign in the Western Hemisphere. Confusingly, the convention of negative for east is also sometimes seen. The preferred convention, that east be positive, is consistent with the right-handed Cartesian coordinate system, with the North Pole up. A specific longitude may then be combined with a specific latitude to give a precise position on the Earth's surface. Longitude at a point may be determined by calculating the time difference between that at its location and coordinated universal time. Since there are 24 hours in a day and 360 degrees in a circle, the sun moves across the sky at a rate of 15 degrees per hour. So if the time zone a person is in is 3 hours ahead of UTC, then that person is near 45 degrees longitude. The word near was used because the point might not be at the center of the time zone. Also, the time zones are defined politically, so their centers and boundaries often do not lie on meridians at multiples of 15 degrees. In order to perform this calculation, however, a person needs to have a chronometer set to UTC and needs to determine local time by solar or astronomical observation. The details are more complex than described here. See the articles on universal time and on the equation of time for more details. Singularity and discontinuity of longitude. Note that the longitude is singular at the poles and calculations that are sufficiently accurate for other positions may be inaccurate at or near the poles. Also, the discontinuity at the plus or minus 180 degrees meridian must be handled with care in calculations. An example is a calculation of east displacement by subtracting two longitudes, which gives the wrong answer if the two positions are on either side of this meridian. To avoid these complexities, consider replacing latitude and longitude with another horizontal position representation in calculation. Plate movement and longitude. The Earth's tectonic plates move relative to one another in different directions at speeds on the order of 50 to 100 mm per year. So points on the Earth's surface on different plates are always in motion relative to one another. For example, the longitudinal difference between a point on the equator in Uganda, on the African plate, and a point on the equator in Ecuador, on the South American plate, is increasing by about 0.0014 arcseconds per year. These tectonic movements likewise affect latitude. If a global reference frame is used, the longitude of a place on the surface will change from year to year. To minimize this change, when dealing just with points on a single plate, a different reference frame can be used, whose coordinates are fixed to a particular plate, such as 83 Namibian dollars for North America or ETRS 89 for Europe. Length of a degree of longitude. The length of a degree of longitude depends only on the radius of a circle of latitude. For a sphere of radius A, that radius at latitude phi is times A, and the length of a 1 degree arc along a circle of latitude is when the Earth is modeled by an ellipsoid. This arc length becomes where E, the eccentricity of the ellipsoid, is related to the major and minor axes by an alternative formula is where cos phi decreases from 1 at the equator to 0 at the poles. So the length of a degree of longitude decreases likewise. This contrasts with the small increase in the length of a degree of latitude, equator to pole. The table shows both for the WGS 84 ellipsoid with R equals 6,378,137.0 meters and BE equals 6,356,752.3142 meters. Note that the distance between 2 points 1 degree apart on the same circle of latitude, measured along that circle of latitude, is slightly more than the shortest distance between those points. The difference is less than 0.6 meters. Longitude on bodies other than Earth. Planetary coordinate systems are defined relative to their mean axis of rotation and various definitions of longitude depending on the body. The longitude systems of most of those bodies with observable rigid surfaces have been defined by references to a surface feature such as a crater. The North Pole is that pole of rotation that lies on the north side of the invariable plane of the solar system. The location of the prime meridian as well as the position of body's north pole on the celestial sphere may vary with time due to precession of the axis of rotation of the planet. If the position angle of the body's prime meridian increases with time, the body has a direct rotation, otherwise the rotation is said to be retrograde. In the absence of other information, the axis of rotation is assumed to be normal to the mean orbital plane. Mercury and most of the satellites are in this category. For many of the satellites, it is assumed that the rotation rate is equal to the mean orbital period. In the case of the giant planets, since their surface features are constantly changing and moving at various rates, the rotation of their magnetic fields is used as a reference instead. In the case of the Sun, even this criterion fails, and an agreed-upon value for the rotation of its equator is used instead. For planetographic longitude, west longitudes are used when the rotation is prograde, and east longitudes when the rotation is retrograde. In simpler terms, imagine a distant, non-orbiting observer viewing a planet as it rotates. Also suppose that this observer is within the plane of the planet's equator. A point on the equator that passes directly in front of this observer later in time has a higher planetographic longitude than a point that did so earlier in time. However, planetocentric longitude is always measured positively to the east, regardless of which way the planet rotates. East is defined as the counterclockwise direction around the planet, as seen from above its north pole, and the north pole is whichever pole more closely aligns with the Earth's north pole. Longitudes traditionally have been written using E or W instead of plus or minus to indicate this polarity. For example, the following all mean the same thing: minus 91 degrees, 91 degrees west, plus 269 degrees, 269 degrees east. The reference surfaces for some planets are ellipsoids of revolution for which the equatorial radius is larger than the polar radius. In other words, they are oblate spheroids. Smaller bodies tend to be better approximated by triaxial ellipsoids. However, triaxial ellipsoids would render many computations more complicated, especially those related to map projections. Many projections would lose their elegant and popular properties. For this reason, spherical reference surfaces are frequently used in mapping programs. The modern standard for maps of Mars is to use planetocentric coordinates. The meridian of Mars is located at Area 0 crater. Tidally locked bodies have a natural reference longitude passing through the point nearest to their parent body. 0 degrees the center of the primary facing hemisphere, 90 degrees the center of the leading hemisphere, 180 degrees the center of the anti-primary hemisphere, and 270 degrees the center of the trailing hemisphere.